Today's resource person is Dr. Shivram Dubey. Dr. Shivram Dubey is an assistant professor in the Department of Information Technology, IIIT Allahabad. In 2016, he obtained his PhD in computer vision and image processing from the IIIT Allahabad. Currently, Dr. Dubey is executing the research project funded by Global Innovation and Technology Alliance India Taiwan. He has also executed the projects funded by DRDO Young Scientist Lab in Artificial Intelligence and Science and Engineering Research Board. He was a recipient of several awards, including Best PhD Award. Computer vision, image processing, deep learning, medical imaging, GAN, and CNN are among his research areas. Over to you, sir.
Thank you very much, Sunil, for the
Yes,
introduction.
welcome, sir. Welcome, sir.
So I have shared the screen. Is it visible?
Yes, sir. Yes, visible, sir.
Okay. Thank you very much. So a warm welcome to all the participants and many congratulations to organizers for organizing such a wonderful uh, this FTP. It's kind of a short-term course on this machine learning. So this particular talk is going to be focused on one particular area, especially in machine learning, which is generative adversarial networks. So I hope that you would have got sufficient background by the time, especially that what is deep learning and what are different deep learning architectures, like there is artificial neural network, convolutional neural network and all. Because this generative adversarial network is built on top of these basic concepts of deep learning. So before going to the actual topic of discussion for today, a quick about IIIT Allahabad. So IIIT Allahabad is one of the 5 MHRD funded Indian Institute of Information Technology, which is situated in Prayagraj. So this is one of the research-led institute and having the status of Institute of National Importance. And we have a computer vision and biometrics laboratory here uh, under Department of Information Technology. So currently our lab is having the research projects which is funded by various funding agencies including DRDO, DST, SCRB, Ministry of Home Affairs and GITA. So at present we have 3 international projects going on. That includes this Indo-German DAT project, Indo-Slovenia project and Indo-Taiwan project. So our lab is also very active in terms of organization of different scientific events that includes short-term course. We used to organize here one short-term course which is called AICTE-ISTE, that is Advances in Deep Architectures for Single Vision and Applications. We are also organizing some conferences. So this year, our lab has taken an initiative to start a new conference, and that conference name is Computer Vision and Machine Intelligence. The CVIP, which is one of the flagship conference in India in computer vision and image processing, that was also organized by this IIIT Allahabad in 2020. Moreover, in Uttar Pradesh, there is a conference which is called UPCon, which is one of the very popular conference. So that was organized at IIIT Allahabad in 2015. And now again this year, we are organizing this conference in December. So in case if you are having some research outcome and if you are looking for some conference to submit your research outcome, basically research paper based on your research outcome, then you are welcome to submit in this conference. That you can reach to this conference from this URL, that is cvmi.iit.ac.in. The conference is going to be held in August, that is 12th to 13th August. And the paper submission deadline is 15th April 2022 in round 1. So coming back to generative adversarial network. So in this particular session, first we are going to have a quick look over the unsupervised learning problem, because this generative adversarial network is kind of a neural network which is used to generate new samples. Means we want to generate new data, but the samples that we want to generate, that should follow, or that should be similar to something which is our data set. For example, suppose if I have a lot of images of Sachin Tendulkar, now I want to generate one new face of, or one new image of Sachin Tendulkar. That will not be the real image, that will be artificially generated image, but it should look like Sachin Tendulkar. Means if anyone see that generated picture, then people should get the impression that this is the original picture. Means it's very difficult to say that this is artificially generated. So generally this problem is solved in unsupervised manner. So first we need to quickly understand, though you might be knowing what is the difference between supervised and unsupervised, but we will again have a quick look. Then in general, what is generative task and how generative adversarial network can be used for generative task, and mathematically how it works, what are different variants, and a very nice application of generative adversarial network for image to image translation. Means where we want to translate image from one domain to another domain. So for example, suppose if I have a sketch of a face, but I want to synthesize the face of that particular person, how that person will look like from the sketch. Means I have an image, I want to produce another image as the output. There is plenty of applications, we will have a quick look on that. And what are the recent trends? So now if you see, there are different mode of learning, like supervised and unsupervised. These supervised and unsupervised, these two modes of learning, they are extreme. Extreme in the sense, in case of the supervised learning, we have the data and we also have the associated ground truth labels. That label can be in any form. A label doesn't mean always the class label. So if that is a classification problem, then that label is a class label. But even we can have many other problems in machine learning, which is not classification problem, but still those problems are supervised problem. An unsupervised problem or unsupervised learning mechanism is another extreme where we have the data, but we do not have any ground truth information, any ground truth label we do not have. There are many other learning modes in between supervised and unsupervised, like we have weakly supervised, we have self-supervised, we have pseudo-supervised. So there are many other supervised this learning framework. So we are not going in very detail in that direction, but there we will have some sort of supervision some way. So, but in general, if you see in supervised learning problem, we have the data. Data is represented by X here. We have the label, which is represented by Y. And our goal here is to find out a function. And if I give X as the input to that function, it should produce the output, which is very close to Y. And there could be different examples like classification, regression, detection, semantic segmentation, image captioning, etc. Suppose if it is a classification problem, then we have the image, we have the class label for the entire image. So that is the classification problem. Suppose someone is having object detection problem, then we have the image as the input, but what is our ground truth label here? The ground truth label here is the bounding box coordinate of different objects that we have, and what is the object inside that bounding box. So these are going to serve as the ground truth labels for this problem. Suppose if we talk about semantic segmentation, where we want to find out, we want to find out the area which is semantically having the similar meaning in the same bucket or in the same category. So there, this problem we can also solve like a supervised problem, where we can say we want to give some color coding to each pixel of the image, and and we have some fixed number of color codings based on different number of objects that we can have, including the backgrounds. Like image captioning, this could be also one of the supervised learning problem, where we have an image and we want to generate a very short caption that can describe that image very well. So at the time of training, we can have the image and some sample captions for that image as the ground truth, and then we can learn this mapping. So again, this is the supervised learning problem. So now let's have a look over unsupervised learning problems, where we have only data, we do not have any ground truth labels. If we have only data, then what could be our goal? What we can do with that data? So if there is no ground truth information, then what we can do? Basically, we can try to understand some property of the data. We can try to find out the relation among the data. We can exploit such things to do some meaningful task. For example, suppose if we want to do the clustering, means I have the data, I want to divide the data into 3 parts or 4 parts, 5 parts, 100 parts, and all the data means all, suppose if this is images, all the images which comes into one part should be sharing some common characteristic. What could be that common characteristic? That might be dependent upon some application where we want to utilize that clustering output. Similarly, if we want to reduce the dimensionality of the data, then we can utilize. If we want to perform the feature learning, then also we can utilize unsupervised learning problem. Let's see how. So I hope all of you might be familiar with this very popular k-means clustering technique, where we have the number of clusters to be known in prior, and then we just initialize the cluster centers randomly initially, and then we divide all the samples. We basically associate all the samples with the nearest cluster center, and then again we found the cluster center by taking the centroid, and this process actually repeats in an iterative fashion. And once there is no movement of the centroid, then basically we will say that now we have reached the optima, and we will have that many number of clusters. Dimensionality reduction, PCA, principal component analysis. This is very popular technique which is used for dimensionality reduction, which tries to find out the principal components, and basically we can neglect a big. So most of the information that we have in the data, that can be represented in the a smaller number of principal components. So basically we can throw out rest of the data which is mostly redundant, and that's how we can reduce the dimensionality of the data. But again, this is unsupervised because we do not have any ground truth label. Another example of unsupervised learning is generative adversarial network. In generative adversarial network, what we want to do, if we have some database, in that database we have a lot of pictures of something, our goal here is to generate a new sample in that data set by seeing that, okay, what are the existing samples? Can we generate a new sample or a new image in that data set which should be very similar to the existing images? Means semantically we can say this is having the similar meaning as we have in the original data set. So the idea here is, and how we can do that? So if we can somehow try to learn, if somehow we try to learn what is the distribution, what is the distribution of the data set that we have, if we can learn that distribution, then it is possible that we can generate a new sample in that distribution. So how we can learn that distribution, that task is going to be done by a network. This network is again a deep learning. It can be a deep learning model or non-deep learning model. It can be any model, but at present deep learning models are giving better results because they are very powerful. They are having millions of parameters inside that can be tuned, that can be learned. So ultimately, we will have a mapping function, and what that mapping function will do, if I give a random vector as the input, then it will generate a new sample as the output. Okay, then someone can say that, okay, why we should give the random vector as the input? So what happens if we have a network? If you have any deep learning model, your model is already trained. You have the trained parameters. So if you are giving some input to your network, whatever input is required, it will produce some output. If you give the same input again, then the output which will be generated will be the same as the previous output. It means that if we keep giving the same input every time, then the model will generate same output. So if we do not have any randomness somewhere in this entire generative task, then we will end up with generating only a single new sample. We cannot generate more than one sample. So that's where this randomness comes into the picture, where if we give different inputs, then we will be able to generate different outputs. It means that now we can generate many number of new samples just by varying the random noise or the random vector which we are giving as the input to the generator network. So here basically we want to learn this distribution. Going forward, there is a type of network which is also called autoencoder, which is very popular. And what this autoencoder tries to do, this autoencoder is also one of the unsupervised learning problem, or one unsupervised learning mechanism, where we want to learn the representative feature of some input data. So what is the meaning of representative feature? So basically we want to represent the input image into some latent space where which can be low dimensional, which can have better compactness, and which can have better robustness, which can have better discriminative ability. So all these properties can be availed in this feature representation. And if you go back some 1 decade, then in most of the time whatever people were doing, that was manual extraction of the features and then using some machine learning tools on top of that. But now this feature extraction process also is being dealt with these deep learning models. So what is this autoencoder? Autoencoder is having an encoder network, and what that network will try to do, it will take some image, that is the input data X as the input, and then it will generate some features from that data or from that image. And what we want this feature to be a good representation of the input data. But the problem here is that, first of all, what is this encoder? So this encoder can be any mapping function. It can be combination of linear and nonlinear functions. It can be a simple artificial neural network, or even it can be a convolutional neural network, depending upon what type of input data we have, like images. But usually Z is smaller than X in terms of dimensionality, because if we have to perform image matching and if we have a large data set, then performing the matching directly on the images or raw pixel values might not be efficient. So that's where doing the matching by utilizing its feature representation is an effective process, efficient process. What and we want to capture some meaningful features. So that's what is one of the important thing. But what is the problem in this particular setup here? Means we have a network, and if you're familiar with the deep learning models, then how these deep learning models are getting trained. or in general how any parametric model is getting trained. Parametric model means there are some parameters which has to be trained. So if there are simpler problem, we can find out closed form expression just by doing the normal optimization. But many times when we have a complex network, when we have many number of parameters, like if I have a million number of parameters, then in that scenario, it is not feasible to find out the closed form solution. Then we have to go for the approximate solution. And the usual way that people are utilizing nowadays to solve this problem is to train your model using gradient descent optimization technique. And how this gradient descent optimization technique is working, we first initialize those parameters randomly. There are different initialization techniques, but every initialization techniques make use of the random initialization. So we will utilize the parameters randomly, and then we will see that how well that model is performing on our training data. And if it is not performing well, there will be now some measurement of how well or how bad it is performing. And that's where, if you see in deep learning, you will find a concept of loss function. So the loss function is nothing but the measurement of how bad your model is performing. Ideally, we want loss to be zero. How loss is computed? That completely depends upon what problem you are solving. Suppose if our problem is a classification problem, then we can utilize cross entropy loss, or even there is a SVM loss which is called hinge loss. We can utilize hinge loss. But what these losses are actually doing, these losses are nothing but they are trying to see what you wanted to, what was your ground truth that you wanted to predict or you wanted to produce, and finally what you have produced. And then somehow it tries to find out the error between that. And ultimately we want to minimize that error over the time. Means now initially we have initialized all the parameters of our encoder network randomly, and then we will try to measure that how well or how bad it is performing, and then we will try to improve our network by updating the parameters, by updating the parameters with this information that when I have done a forward computation, then what was the performance of my model. So that's where, if you talk about any supervised learning problem, then this task is very simple because we have the ground truth label with us. Okay, I wanted to classify this image into cat category, but it has classified into dog category. And then what is the class score for the dog category, what is the class score for the cat category. Based on that we can find out some error function, and that is very easy to. But then, and then after that we will update the parameters just by utilizing what is the gradient of my error function with respect to that parameter. And we know that, suppose if I say you that okay, y is equals to fx, then suppose if x is equals to x naught, then y is equals to y naught at that time. And if I am going to make x is equals to x naught plus delta, what impact it will make in y, that we can find out very easily just by finding out what is the del y by del x. If you know what is the derivative of y with respect to derivative of x, then we can say with the guarantee that if I am trying to increase or decrease some small value in my input x, what impact it is going to make on y. So the same way this gradient descent works, because we know that ultimately what is the entire function, how final error function, how final objective function is dependent upon any of the parameter in my network. That information is known to us because we know what is the entire function. So based on that, actually we can update the parameter. But now, what is the problem when it comes to unsupervised learning? Now, in case of the unsupervised learning, now how to judge, how to say that how well or how bad my model is performing. So here, if you see, I have suppose a picture of cat, that is input data X. I have given that as the input to the encoder, and because I have not trained the model yet, I'm going to train my model. So initially, all the parameters of the encoder is random. And if the parameters of the encoder is random and it is generating a feature vector which is represented by Z, then most likely that feature vector will be also random. Means that feature vector might not be very good. But the problem is how to quantify it, how to measure that the quality of this feature is not good. Is it possible to measure? Because if we can measure it, then only we can compute the gradient of that function, that loss with respect to my parameter in encoder. Then only I can update the parameters in such a way that next time with guarantee the loss should decrease. So that's where in most of the time when we do this unsupervised learning problem, then we need to find out some other mean of computing this error. And when it comes to autoencoder, then autoencoder, what it does, it takes help of one more network that is called decoder. What it tries to do, in order to measure that how well or bad this encoder is performing, it will have one more network now, which is called decoder. This decoder is also a parametric model. It will also have the parameter. It will be also trained. But what is the purpose of the decoder is to take the feature which was generated as the input and to produce or to reconstruct the original input data. Means if I had a cat, picture of the cat as the input, I have extracted the features using encoder. Now there is another network decoder which will take this feature and it will try to reconstruct the picture of cat. Why we are doing this? Because now after reconstruction, now we can have some base to compare. Means X was my actual input and now this X cap is the reconstructed version of that input. Ideally what we want here, ideally we want the X cap to be very similar to X. Means if Z is a good representation of X, then from that representation, we will be able to reconstruct the original input. So basically, what we will do now we can compute the error between X and X cap. And then we will try to minimize this error. And in that way, we can simply first train the decoder and then encoder means in that particular manner. So now what is the good thing here? The good thing is with an autoencoder that in order to train, and what happens, see, once training is done, we no longer require this decoder. We can just remove it. So once training is done, now we have a trained model which is encoder. You just give any input image, it will produce its feature as the output, and then we can use that feature as the very good feature vector, and we can have any classifier on top of that, and we can just train any classifier on top of that. But what is the main thing here that is the key point, and that key point which is exploited in generative adversarial network as well is, in case of the unsupervised learning problem, we wanted to train an encoder network for feature learning, but we do not find any way to measure the goodness or badness of the output of that network. Then autoencoder takes the help of another network which is called decoder too, in order to facilitate the training of the encoder. It means that it so happen in deep learning that in order to train something that we want to use at the testing time, we may utilize some additional network, some additional information at the time of training that might not be required at the time of testing. So the similar concept is also exploited by generative adversarial network. So in general, as I mentioned earlier, what is generative task? So generative task is nothing but to learn the representation in such a way that we can produce the new images in a training set. So this is unsupervised learning problem. We can have the conditional generation as well, like okay, I want to generate all the pictures of dog, all the pictures of cats, so that could be conditional. Or even we can have conditional images, like okay, I have an image of suppose this black and white image, and I want to produce the color image. For that, I have the sketch of some object I want to produce, how it will look like. I have image taken to the daytime, how it will look like in the night time. So these things is these applications are also conditional applications where we have some additional input. So we will come to that after some time. Okay, so for generative task, what we want to do, we need an architecture that can generate an image. Okay, so now if you look at again autoencoder that we have just seen. So in autoencoder, if you focus on the second part, which is the decoder. So what a decoder is trying to do? Decoder is having Decoder is having a vector, a feature vector z as the input, and it tries to generate an image as the output. So it means that we can exploit this fact of autoencoder, which is decoder. We can use this decoder as a generator. So now what we can say, if I take the decoder part of autoencoder, then I can say that okay, I can give a vector as the input, then it will produce an image as the output. But in case of the autoencoder, that vector was the output of the encoder. But in case of the generative task, we do not have the encoder part. Encoder part is not there. If encoder part is not there, from where we will get that vector, which is the input to the decoder? So then we will say that, okay, then why not to take a random vector? So what now we can do? Let's take a random vector as the input to the decoder, and then this decoder will produce an image as the output. Means now a random noise. So random noise means this is just a random input, which is termed as a random noise. So a random vector as the input given to the generator network. Now this decoder that earlier we were talking in autoencoder is now transformed into a generator network. Ideally, the decoder there and the generator here both wants to do the same task. Means both are getting a vector as the input and both wants to produce an image as the output. But in case of the autoencoder, that feature vector was generated by some other network which was encoder. But in case of the generative adversarial network, the input to this generator is now a random noise or a random vector, and we want to produce an image, and that image should follow the distribution of our actual training data. Means I have a lot of pictures of cars, I want to produce a new picture of the car, and that car should be very similar to all the pictures of the car that I have. So now this generator network can be any mapping function, and in today's scenarios, this is nothing but a up convolutional neural network, because we have a random vector which has the lower dimensionality, and we want to produce some image which is having the higher dimensionality. So now what we need, if you again recall, in case of the autoencoder, we had the encoder was the main thing there. We wanted to train the encoder. In order to facilitate the training of the encoder, we took the help of another network which was decoder. But in case of the generative adversarial network, what is our main network? Our main network is this generator network, because this generator network is going to generate some new sample. But now again, when I'm going to start training of my generator network, then all the parameters in the generator network will be initialized randomly. I have input also as a random vector. All the parameters are also initialized randomly. Then what will happen? It will produce an image which is also having random values as the output. It means that because everything is random, so the output image will be also a random image. And if it is a random image, then obviously it is not going to be very similar to the images that I have in my training data. But question comes, how to say this, how to quantify this, how to find out some function which can say that how close this new image which is generated, how close it is with respect to your training data, your training images, or in general, the distribution of your training images. So that's what we wanted to learn. So ideally, what we want to do, we have some training data with us. There is a probability density function for that training data. Let's represent that by P data. And suppose if my training data is sampled from that probability distribution, and this is the probability distribution of our actual training data. And when we have a generator network, and that generator network is, if I give a lot of inputs, even initially when my uh, parameters of the generator networks are random, if I give a lot of inputs random, because inputs are also random vector, if I give a lot of vectors randomly sampled as the input to that generator network, it will produce a lot of images. Those images might not be very similar to this, but those images should also follow some distribution. And suppose that distribution is represented by P model, that probability distribution is represented by P model. So ideally, now what we want slowly our generator network to learn the parameters in such a way that the probability distribution of the generated samples, which is represented by P model, to be very close to the probability distribution of the actual training data. See, we cannot change P data because that is fixed. We have a fixed training data set. So its probability distribution is fixed. What we can change, we can only change the probability distribution of the generated samples, which is generated by the generator network. How we can do that? It means that now, in fact, if we can find out some way to say that what is the difference, what is the error between P data and P model, then we can solve this problem. Then we can have some function, and that function we can optimize. So how this is done? So this is done with the help of another network which is called Discriminator Network. Now we will have one more network. And what is the task of the Discriminator Network? Discriminator Network tries to distinguish the real samples from the generated samples. Means it tries to say that if something is the input, this input is from the actual training data, or this input is coming from the generated distribution of the generator network. So now we are going to have now two network. Actually, we want to have only generator network at the test time, right? Generator discriminator network is not required at the test time. We want to have only generator network, and the purpose of generator network is to take a random vector as the input and produce a new sample as the output. That new sample should be very close to the samples that I have in my training set. But how we can learn the distribution of the training set? In order to learn the distribution of the training set, which is P data, we now take help of another network, which is the discriminated network. Now, the if I give any sample from actual training data as the input to this discriminated network, then it should classify that one into a real category. But if I give the generated sample, which is generated by the generator network, as the input to the discriminator network, which is represented by D here, then it should classify that input into the fake category. But at the same time, what generator network wants the output image produced by the generator network to be very close to the real images in our training data set, such that discriminator can be fooled. Means discriminators should get the impression that this generated image comes from the actual training data. Means the quality of that generated image, if it is improved in such a way that the discriminator network gets confused between the actual training data and the generated data, then actually generator will be very happy. So based on this particular phenomena that generator wants to produce such an image which can fool the discriminator network, means discriminator network will classify that image in real category instead of classifying into the fake category, then generator network will be happy. But when discriminator network will be happy, because the purpose of the discriminator is to classify the generated sample into the fake category and actual sample into the real category. If it achieves this task, then it will be happy. So based on in which scenario generated network and discriminated network will be happy, or basically will be giving us a smaller error, we can now have the objective function. So ultimately what is happening here? We have a random noise as the input to the generator network. Generator network will produce some images, and these images will be treated as fake images, means generated images. We will also have the actual images, which is treated as the real images. And if we give these images as the input to the discriminator network, then discriminator network will try to classify that into real or fake category. So again, this again, so how we can, is there any question so far?
Yes, if anyone have any query, please ask.
Okay. Okay, now let's try to understand the same thing mathematically. So what is happening? We have our data set, means we have a lot of images in our training data set. We have just images, there is no label. So if we take the samples from that training distribution, then that sample will be given as the input to the discriminator network. The output of the discriminator network is the probability of being real sample. It means that if we give any input to the discriminator network, and if it produces the output which is close to 1, because probability is always in between 0 and 1, if the output of the discriminator is close to 1, it means that that input for which the output of the discriminator is close to 1, discriminator thinks that that input is coming from the real category. So because we have a real data set which is given to the discriminator, so discriminator always try to produce the output near to 1 for all these samples which is coming from the real data. But at the same time, we also have the samples which is generated by the generator network Z based on some random input noise Z. So if we sample from the generated distribution, and if we give that as the input to the discriminator, then for that sample or that generated sample, generator wants different output, discriminator wants different output. Discriminator wants to classify the generated sample into the fake category. Then in that scenario, the output of the discriminator, which is nothing but probability for being real, because discriminator wants to classify that generated sample into the fake category, so the probability for being real will be close to 0. If probability for being real is close to 0, it means probability for being fake will be 1 minus that, which will be close to 1. But at the same time, for the same generated output, for the same generated sample, the generator network wants discriminator to fool, means generator network wants that discriminator should output or should classify the generated sample into the real category. It means that the probability, the output probability of the discriminator network for that generated sample, generator wants it should be close to 1. So it means generator tries to make the output of the discriminator for generated sample near to 1, but at the same time, for the same input, discriminator wants to do the opposite thing. And that's where this entire network is treated as the adversarial network, because now for the same input, there are two different networks. They want to behave differently for the same input, and it is actually adversarial. That's why this network is also termed as generative adversarial network. Means we have a generated sample. On that generated sample, there are adversarial way of working of different networks, which is generated and discriminated networks. So based on that, basically we can also model the objective function of the GAN, and the objective function of the GAN can be written like this, that the output of the discriminator is represented by dx, where x is sampled from the real data. This p data is real data. This e is basically representing the expectation, because we are actually taking the samples from the distribution, and we compute the log of that probability. So this is log likelihood, so log of dx. And when a random vector is sampled from some probability distribution, which is represented by P, and it is given as the input to generator network, then the generated sample is represented by ZZ, which again given as the input to the discriminator network. Then the output of the discriminator network for the generated sample will be represented by D of ZZ. But here we are considering log 1 minus D of ZZ. Why we are considering log 1 minus D of ZZ? Because this particular function is written from the perspective of the discriminator network. Discriminator networks wants to produce 1 for the real samples, but ZZ is the fake sample. Then from discriminator perspective, this D of ZZ should be close to 0. But from a network perspective, this entire optimization can be either maximization or minimization. So it is written for the maximization. So in that scenario, this D of ZZ, if you again recall, D of ZZ has to be minimized with respect to the discriminator. But if you see D of X has to be maximized, so both should be same, either maximization or minimization. That's why we write here log 1 minus D of ZZ, because if D of ZZ is a minimization, then 1 minus D of ZZ will become maximization. But at the same time, this entire objective function will become a minimization problem if we consider from the perspective of the generator network. Because what generator network wants? Generator network wants D of ZZ to be close to 1. It means 1 minus D of ZZ to be close to 0. Then from the perspective of generator, it will become a minimization problem. It means that the same objective function now, this discriminator wants to maximize, but generator wants to minimize. So it will become kind of a mini-max game where generator and discriminator both will be jointly trained by the minimization and maximization. What will be the final impact? So suppose if we are able to do that, then basically we can achieve Nash equilibrium. That it means if we are able to optimize this objective function, then effectively we will be minimizing this JS divergence between P data and P generated samples, means the distribution of actual and generated samples. And when these distributions will become exactly equal, then at that time we can get the Nash equilibrium, means then the quality of the images that we generate will be very good. So generally during the training, there is an alternate training because this is a maximization problem for discriminator. So instead of using gradient descent, gradient ascent will be utilized there, and because minimization problem for the generator, then gradient descent will be utilized for the generator network. And based on that, this model will be trained. There is a variant of the so this is generative adversarial network. There is a variant of this generative adversarial network which is called non-saturating GAN. So what it tries to do, instead of considering the same objective function for both generator and discriminator, it basically consider different objective function for generator and discriminator. So for example, this objective function that we have, that log of dx plus log of 1 minus d of zz, the same objective function will be used for discriminator. But when it comes to the generator, then instead of using log 1 minus d of zz, log d of zz will be used. And why? Because what happens, so when our model, in the initial stage of the training of our model is having random values of the parameters, then the quality of the generated images are not very good. It means that when the probability when the probability of being classified into the real category is not so good, means when it is close to zero in the initial stage of the training, and if we observe the behavior of the objective function like log 1 minus d of zz, so you can see this second plot here. So in this scenario, what happens? The quality of the gradient, or amount of the gradient that we could get in the region where the probability is close to zero. It means that in the initial stage of the training, then that gradient is not very good because we have kind of a steep function there. So if you see here, so here we have smaller gradients, but here we have larger gradients. So when means in the initial stage of the training, when we have to train faster, in that stage, this function behaves in a different way. The quality of the gradient is poor. So basically, it faces the problem. Means if you utilize this vanilla version of the generative adversarial network, where you use maximization over discriminator and minimization over the generator, then what will happen? For longer number of iterations, you will find out that your model is producing not so good samples. It will take many number of iterations for your GAN to start producing even some appealing result. Because what happens in those scenarios, the quality of the gradient is not very good, and that is going to hamper the learning of the entire network. But if we treat that problem as a minimization problem just by using this log d of zz, so now we can see when the quality of images, generated images, are not very good, and discriminator produces very low probability for being classified into the real category, at that time we have very high gradient. It means that the model will be trained much faster in the initial stage of the training, and it should quickly start producing better quality images. So in general, how this training happens, we repeat for case steps. First, we update the discriminator. So we take the samples, which is the random vectors, and we take the samples from the real images. And after that, it utilizes stochastic gradient is ascent on this discriminator. And after that, we need to update the generators. Then again, we will sample. Means updation of the discriminator and generator will happens in an alternative fashion. So again, we will update the generator. For that, we need to again take samples, noise samples, and then we need to compute the stochastic. We need to apply stochastic gradient ascent based on the objective function, which is log d of zm here, and we will take the average over all the samples which is taken, because there is no real image involved in updation of the generator, so this is not required. So many times we simply just use to take this value of k as 1, means every time we update one discriminator, then we update generator, then discriminator, then generator. But that is not hard and fast rule. Even some people tries to update discriminator even more than once before updating the generator, or update generator more than once before updating again this discriminator. So vice versa. So conceptually, what this GAN is trying to do? So conceptually, we have a random vector as the input to this generator. Generator produces some output image. That output image is given to the discriminator, and discriminator produces the probability of that generator output to be classified into the real category. And if the quality of this GZ is very good, then this discriminator will get fooled and it will generate very high probability for real. But when the quality of this GZ is not very good, then the task of that discriminator is very easy, and it will easily find out that, okay, this is coming from the fake distribution, and it will produce the probability close to zero. And when this original, when the real data comes, then this discriminator produces the output of the probability to be classified into the real category, which will be close to 1. So that's how basically this entire training happens for this generative adversarial network. At this time, we don't need the discriminator network. We only need the trained generator network. Then if you have a trained generator network, just give any random vector as the input, and it will be able to produce any new sample, which is represented by ZZ as the output. So here are some generated samples by using the original generative adversarial network from MNIST digits. So these are the generated samples here. If you see the second last column and the last column, so second last column is having means first column to the second last column. These are having the generated samples, and the last column has the real images, which is nearest to the samples in the second last column. That is this 9. This is 9. Means if you just find out the best matching images in the data set. So basically, if you see, this is generating very similar images in terms of these digits. In terms of face also, it is able to generate some face. Quality of the generated faces are not very good if we just use this vanilla version of generative adversarial network, but we will see that there are many improved variants of the GAN, which is able to produce very high quality faces. So another improvement that happens in GAN was DC GAN, means deep convolutional network-based generative adversarial network, where a deeper architecture is used. And so this was one of early and very influential convolutional architecture for generative task. There was discriminated network, and having some properties like it doesn't use pooling layer, it uses only strided convolutions, and it uses leaky ReLU activation function because we have to use some activation function for nonlinearity. It uses only one fully connected layer just before the softmax, because we have a classifier in this discriminated network, which is a binary classifier between real and fake category, and also uses batch normalization after most of the layers for generalization. These are some generated samples just after one epoch of the training, and we can see it is able to at least generate some layout, and these are bedroom scenario. So at least it is able to generate some layout, not very good. After 5 epochs, some details are also coming very well, and after completely training the model, now you can see these are the generated images by this DC GAN after training, and these are looking kind of very realistic images. Means if we see these images, and if someone doesn't say you that these are generated images, then you might be thinking that, okay, these images might be the real images. So in general, this generative adversarial network also faces some issues, like there is a stability issue because there is a optimization problem of this minimax, where one network wants to turn down another network. So many times, basically, it faces these problems while we are training. And sometimes it is also very sensitive to the hyperparameter selection, like what learning rate you are using, which particular loss function you are using, and what type of layers you are using. So it is all we have to also be very careful when we are designing this. Another issue with generative adversarial network is called mode collapse, where what happens, this network learns in such a way that it is learning very good for some images of your training data, but for some part of the data, it is not able to learn. Means, suppose if we are having five, six categories, pictures of five, six categories, and it is able to learn very well to produce the cat, it is able to learn very well to produce the faces, but somehow it is not able to produce dog in such a way. So that happens. This problem is mode collapse problem, when instead of learning the overall distribution of the training data, if generative adversarial networks only tries to learn a part or the subset of that distribution, then it actually stuck into the mode collapse problem. There are many GAN flavors which tries to improve these drawbacks of generative adversarial network, like there is WGAN and improved WGAN. So WGAN is called Wasserstein GAN, and there is a least square GAN. So it tries to improve. So like WGAN, what it does, it actually get rid of the lockdown. So now if you see in the original GAN objective function, that objective function was log dx plus log 1 minus d of zz. But what this Wasserstein GAN is doing, actually, it is based on uh, this Earth mover distance, basically, which tries to kind of minimizing this GS divergence, which is nothing but just dropping this log term, just taking the probability value itself and the probability probability of real sample, that is dx, and the probability of generated sample d of zz. So what we want, so now it basically takes the difference of these two terms. And when it comes to the generator networks, then what we want from the generator network point of view, we want d of zz also to be close to 1. It means that because d of x is also d of x is close to 1, because these are the real samples. But what we want d of zz also to be close to 1 from the generator perspective. So it means that if we listen to the generator, then generator wants this dx minus d of zz actually close to 0. But when we talk about the discriminator, discriminator wants d of zz to be close to 0, but d of x close to 1. It means that discriminator wants d of x minus d of zz close to 1. It means from discriminator perspective, it will become a maximization problem, and from generator perspective, it will become a minimization problem. So what is the good thing with this Wasserstein GAN is when we have the log term, so this is basically giving this distribution. So we have the real distribution, which is represented by this blue. We have the distribution of the generated sample, which is represented by this green line, this green curve here. So now we can see this GAN discriminator, what it tries to do, it tries to basically it tries to classify this real into the, for real it tries to generate 1 as the output, and for fake it tries to generate output as 0. And it means that if you talk about the gradient, then again that gradient will be much saturated. If discriminator is performing very well, then that gradient will be much saturated. It means that the quality of gradient will not be very good. But if WGAN is considered, because WGAN is dx minus, because WGAN is dx minus d of zz. In that particular scenario, it is going to be somewhere linear, and that is going to be a good thing because now we will have a good gradient. And when we are going to have good gradient, then actually the training of generator and discriminator both will improve, and that's what is the benefit. Means better gradient and more stable training by this WGAN. Even objective function is also highly correlated, highly related to the quality of generated output. There is a gradient, there is a WGAN with gradient penalty. So it is exactly same as the Wasserstein GAN, but they make one more constraint where they want to have this unit norm gradient penalty. Means if you take the norm of the gradient, it should be unit. If it is not there, then we will take the error. That error is nothing but that is the square of the difference between the norm of the gradient and this 1, because we want to compare it with 1. So here some results are being shown using DC GAN, LS GAN we have not seen, it will come to next, and WGAN and WGAN with gradient penalty. So then people found that gradient GAN, WGAN with gradient penalty, that performs very well as compared to other variants of this GAN. LS GAN, which is called least square GAN, it tries to minimize the Pearson divergence, which is nothing but, so we want to push discriminated response on real close to 1. So basically we will take the difference from 1 and square it. Similarly, push response on generated data close to 0. So we'll take the square. So what is the benefit of having the square? So suppose if you have y is equals to x, and if I tell you that, can you find out the minima? It's very difficult to find out the minima there, because if you are using gradient descent mechanism, you will never find minima because minima is minus infinity. But the same problem, if I make it a square, y is equals to x square, if I tell you that, okay, can you find out minima? We can find out because that is quadratic in nature. So that's where when we bring a square in objective function, that it gives us some inherited benefit in terms of the quadratic nature. So that's where this LS GAN generally performs better than the vanilla version of the GAN. So again, it can produce higher quality images, and even it is more stable and resistant to mode collapse as compared to regular GANs. So there are other variants also. We may not go very deeper, but we can just touch it upon, like progressive GAN. So progressive GAN is used to generate the images at high resolution, and it tries to train in a progressive manner. Means first it will do the training on a small resolution like 4 cross 4 for some time, and once the model is trained for 4 cross 4, then the same model will be extended by adding few more layers such that it can produce 8 cross 8 output. Then again the training will happen, and once our model is able to produce some good images even in 8 cross 8 resolution, then again we will add additional layers, and then we will produce 16 cross 16, then 32 cross 32, then 64 cross 64, then 120 cross 128, like that. So every time, if you see, we are producing the output image, and size is getting doubled, 4 cross 4, then 8 cross 8, 16 cross 16, 32. Basically, so first it tries to train at lower resolution, and then it uses that information in a progressive manner to train the other layers, or train the additional layers that can generate from the previous resolution to the next resolution. And that's how it is able to produce very high quality images. But the drawback with the progressive GAN, it takes huge amount of time and resources in the training, because you have to train your model at uh, different resolutions, various resolutions, and that is going to increase the training time. These are some output images using progressive GAN at 256 cross 256 resolution, and we can see these are very good quality images which is generated by this. Another variant of generative adversarial network, and which became very popular, that was style GAN, because using style GAN we can do a lot of things. And nowadays even many work which people are trying to do, where people are trying to do something very differently, they are actually making use of this style GAN. So, and why this is popular? Because using a style GAN, actually we can produce some sort of a style, and that style can be encoded. That style can be encoded automatically by a style encoder network, which is called the mapping network. So what happens? So if you see, this is the traditional progressive GAN. So style GAN uses progressive GAN as the backbone. It is built upon the progressive GAN, but what it tries to do? So first of all, it tries to learn a style, means the encoding for the style which is represented by W. So there will be a mapping network. That network is also a trainable network. This network will take your input like something, let's say Latin space Z, which is represented here, and then it produces a style which is W, and then that style will be given as the input at different stages of the synthesis network, which is nothing but the generator network of this progressive GAN. There is a noise vector also. Noise vector is given at different stages, and the purpose of giving noise vector to generate different and different examples. Every time you run the network, then it will generate a different sample, different sample, different sample. Then because there is some stochasticity there. So these are some generated images of style GAN. So again, we can see we can synthesize very high resolution images, and even we can have some styles. For example, suppose you want to have the styles like a smile, you want to have different expressions as the style, or you want to have different hairstyles. So all these things can be taken care by this style GAN. These are some generated samples using a style GAN of bedroom scenarios. Again, we can see these are very, very realistic images. Cars, these are generated samples. It looks very real. So this is about generative adversarial network as a generative model, but many times in real life scenario, we want to generate something, we want to generate images, but those generation are dependent upon something. Like suppose if I want to transform a sketch into the actual image, then what happens? Basically, we want to produce some output in the actual images, means actual domain, but instead of using the random vector as the input, here we can see some condition as the input, and this condition is basically nothing but or this input is nothing but a sketch here. So in general, we can say image to image translation, where we have one image as the input and we would like to produce another image as the output. So there again, we can have two scenario. One is the paired scenario. In paired scenario, we have the exactly same location, exactly same object, but we can also have unpaired scenario where we might have a different uh, appearances, but we may want to transform some kind of a style, some kind of a course information. So all these things we want to transform. So the very popular approach which is used for image-to-image translation in paired scenario is pix-to-pix model, which is actually built upon conditional GAN. For unpaired, we have cycle consistent adversarial network, which is called cycle GAN. The species GAN is proposed by us, which we have proposed for the paired image-to-image translation. So how it works? So this is very similar to what we have seen in case of the generative adversarial network, where we have a random vector as the input, but what changes we are making now, we are replacing that random vector by this sketch image, means the image in our source domain, and then we will generate new image into the target domain. We also have the ground truth image. We also have the images in the target domain, which will serve as the real category. So the same thing, So now sketch as the input, generating a new image as the output. If we give that new image as the input to the discriminator, it should classify into the fake. But if we give any real sample, then it should classify into the real. But generator wants this discriminator output for GX to be real. So the exactly same thing that we have seen earlier. So one thing also which is pix-to-pix model, which is built upon conditional GAN, is also trying to use the actual input along with the generated sample as well as the real sample when it comes to the discriminator network. This means discriminator network will receive the stack of means both generated sample and the actual input. Both are going to just stack channel wise and then given as the input to the discriminator network. So this is basically called pix-to-pix model. So these are some output images for different problems. Like if we have labels means the segmentation map, then we can generate the scene that okay what scene might be there. We have the labels here, labels to this bracket means this is the building, black and white to the color, and aerial to map, dim image to the night image, sketch to the actual image. So there are many such applications where this conditional GAN can be utilized or pix-to-pix can be utilized. There is a cycle GAN. The cycle GAN is proposed for unpaired scenario where we do not have the pair scenario. Then in that scenario, what it tries to do, it actually considers a generator network and it considers two generator network. The first generator network tries to transform from X domain to Y domain, and then the transformed image in Y domain will be also transformed back into the original domain, original input domain using another generator network, which is represented by F. Means first X is transformed to Y and then again transformed back to X, and then it's kind of a cyclic nature, and then the transformed back version should be very similar to the actual input, so that loss is computed here, which is called cycle consistency loss. So that happens in from other direction as well, means image from target domain, that is Y, transform to the source domain and again transform to the target domain, and then cycle consistency loss is computed here. So this is the same thing that we have the input image, then cycling. A to B means this is transformation from domain A to domain B. This is horse to zebra. So source domain is horse, target domain is zebra. So A to B. And then again, whatever is the generated image in B domain will be transformed back, means B to A. Then this is cycled version, and then the loss will be computed between these two. The same thing will happen in other domain as well. So again, these are some output images, like if we give this monet, it is generating photo, and if you give the photo, it is generating monet, means both zebra to horse, horse to zebra, summer to winter, winter to summer. The species GAN is one of the approach where we have tried to utilize something called cyclic synthesized loss and perceptual loss. So perceptual loss is something which we compute in the feature domain. So for that, there is pre-trained models that is utilized to generate the features, and then loss is computed in the feature domain. We have used it for this image to image translation, and that is in the thermal domain, to the image domain. So these are some results. There are many other applications of the generative adversarial network, like generating these cartoon characters. Suppose if I just give you a sentence, and if I ask you to generate an image, that image should have similar meaning like we have in the sentence. Means text to image translation. This is a very popular problem nowadays. So if you want to make face as frontal face means I give the face in any random pose, and if I want to make it frontal, then again this problem can be treated as generative adversarial network problem where source domain is a random pose face and the target domain is the frontal face. Face aging, that can be also done using this generative adversarial network. Deraining means our input image is having the rain effect, but in output image we don't want to have that rain. So that's called deraining problem. That can be also solved using this GAN image to image translation. Photo in painting means we have some input image and some portion is not there or corrupted. We want to fill it. That's called in painting problem. So this is again image to image translation, means our input image is an image having some portion missing, and we want to predict that portion in the output image. Super resolution, our input image is having a smaller resolution, we want output images to be in higher resolution. That can be again solved as an image to image translation problem. Dehazing, so if you take a picture in hazy scenario, means foggy scenario, and you want to remove the effect of the fog from the input image, then again it can be treated as image to image translation problem. There are many such applications where this image to image translation problem can be applied. And nowadays, even if you see this virtual try-on means if I just have your picture, then we will be able to synthesize your picture with some other clothes or some other style, pose, these things. And there are plenty of applications and there are plenty of variants also of this generative adversarial network which daily comes into the picture. So this is all about this generative adversarial network and some variants, some properties, and some applications. Now it is open for questions.
Thanks, sir, for exploring about GAN and providing us new knowledge about GAN. I must say this was a wonderful session. Thanks a lot, sir.
Thank you very much, Sunil
Thank
ji.
you, sir. So it was actually a very beautiful session which started from scratch and took us to the level where, we really look forward to actually learning, sir. So if you could just
Yes,
share these, the PPT so that I could put it across to the faculty and the students in this program.
yes, I will say. So I think I have 5 minutes. So let me just have quickly one demo
So,
I created, but I think now there is no much time, but still I can just quickly show it.
sure, sir. Sure, sir.
Okay.
Yes,
So
Richa ma'am, do you have a query? Richa
Yeah,
ma'am, do
yes,
you have a
I
query?
wanted to ask. Yeah, before that, I
Yes,
also
ma'am.
want
Sure.
to say the same that the session was very nice, especially various types of GAN. So I have one question since I am reading GAN that they say that generator and discriminator both are updating themselves, both are improving themselves. Then where does this model converge? If both are using backpropagation to improve themselves?
okay, so what happens? Ideally, when we are running it, then this discriminator network is first tries to learn very fast. So when discriminator network will learn very fast, then the loss for generator will not be that much good. Then generator will again try to learn. When generator will try to learn, then the quality of the generated images will increase. When the quality of generated images will increase, then this discriminator, the loss for discriminator will increase. Then again discriminator will start learning, means further start learning. So like that, it is going to learn always. And if you are going to just continue, then where it is going to get the equilibrium in the sense when half of the time generator is winning, half of the time discriminator is winning. So some time of equilibrium it will achieve after some time if everything goes well. Then in that scenario, the loss for your generator and discriminator both should come to roughly 0.5. Means if the loss for both is getting settled somewhere around 0.5 for generator and discriminator, then you can think that actually your model is able to saturate.
Okay, okay, sir. Thank you so much.
So basically, this particular repository is already available. Even if you just search this pix to pix code in PyTorch, you can find it. So what I have just tried to do it just to run on a very small data set of CUHK. So this particular data set here is, and even this model you can run in Colab very easily. So you can just download it. So for example, I have downloaded this data set CUHK. So it is having this train A, train B. So if you see train A means this will have all these pictures of sketches. So basically these are sketches. Train B, this will be the corresponding picture, but original means this is without a sketch. So now this is the problem of translation from sketch to the real faces. So we also have the test images. So test A. So now our model will, at the testing time, it will take only these sketches as the input, and it will generate the image as the output. Test B will not be used for the testing. It will be only used to find out what is the performance at the test time of our model. So now you can see here this training is happening now. So I have just trained for 10 epochs. Then after that it will run for the test one. But if you go here, what is happening inside this? So basically we are simply just trying to import the drive from this one, and then I'm just giving the path that where my files are basically situated. So after giving this particular path, there is some requirement that I have to install there. So after that, basically it is running one file. What is this file? This file is nothing but train.py. So basically if I go inside this, then I will have so this train.py, this is a file which is kept it here. So if we can open it, then we can find basically the code for this pix-to-pix model inside this. So here we have different training options, and some are by default, some options we are giving as a command line argument. And ultimately, this is a visualizer which works if you are going to basically instead of training in Colab, if you train on your system, then you can also get the visualization of the loss functions, that how basically it varies. So now here you can see there is a model. This model is basically getting trained here, optimize these parameters. So this for I comma data means this is loading of the data set, and based on your batch size, it is going to basically just run this in a loop. And then in this particular loop, it is just trying to optimize the model. So this is running in the epoch, means for how many epochs you want to train. So this is the code here. And now if you see from where it is getting the models. So basically there is a models, import, create models. So inside this, there will be a directory. That directory will have the models. So inside this model, basically, there are different files. So now you can see there is a pix-to-pix model. So if you go in the pix-to-pix model, then you will be able to find out the code for the pix-to-pix model. So ultimately, they will have this this generator and discriminator. Both networks will be defined. It will be initialized, and then so now, for example, here if you see the forward pass, the net G means this is the generator network. It takes real images. The in input real in domain A means sketch, and it produces the fake means in domain B. Then this fake B will be used to compute the losses for both discriminator and generator. So when we have this backward for the discriminator, then we compute the loss for the discriminator. So which is nothing but loss in terms of the fake image, which we are getting, loss in terms of the real, and then taking the average of this. Similarly, when we have the generator network, if we write the backpropagation for that, then we compute the loss for the generator. So loss for the generator here is the generator loss that we have seen, and it also uses L1 loss because this is a paired scenario. So we can also use the concept of autoencoder also along with this in pix-to-pix. If it is not paired scenario, then we cannot use L1 loss here. And one important thing, when discriminator is trained, then there is a detach function which is normally used. So what it tries to do, it tries not to pass the gradient to the generator network when we are training only discriminator network. But when we train generator network, then at that time this detach will not be used. So we have to basically consider this thing. Otherwise, what will happen? It will back propagating in generator also when we are back propagating discriminator. So now we can see here. So this is just trained for 10 epochs, and testing is done here for some images. So after testing, what it is going to do, it is going to generate a new this results directory. Inside the results directory, now it will just all the generated images for testing set will be kept it here. So like these are the generated images. So here you can see, because I have trained only for 10 epochs, so this is not very good. You have to train at least for 200 epochs if you are training this GAN model. So these are generated samples here. So if you see this one, so this is example of mode collapse, means it is not able to learn properly in this 10 number of epochs. Yeah, but if you train longer, then obviously it is going to work. So for some images, if you see, the results are very good. Yeah, this is very good. So yeah, this is about this generative adversarial network. Now, if you have any questions, you can ask.
Yes, anyone have any question? No, sir.
Okay. Okay.
Thanks
So
a lot, sir.
thank you
Thanks a
very
lot,
much.
sir.
Yeah. Yeah. Thank you very much to all the participants for listening, and thank you very much to organizer to giving me this chance to speak on this forum. Thank you very much.
Thanks. Thank you, sir.